Let's talk about one of the most important, most practical challenges in all of machine learning, building a model that doesn't just work on your training data, but actually works out in the wild. This is all about generalization, and the set of tools we use to achieve it is called regularization.
You've probably been here before, right? It's a classic. And honestly, a pretty painful situation. You've spent days, maybe weeks, training a model. The loss is weighed down, your accuracy on the training set is like 99%. It's looking perfect. But then you deploy it to production, you feed it new data, and the performance just completely falls off a cliff. So what's going on?
The villain of our story is a little something called overfitting. This is what happens when your model is, in a way, too smart for its own good. It has so much capacity that it stops learning the general patterns, the signal in your data, and it starts just memorizing the random quirks and noise. It's like a student who memorizes the answers to the practice test but has no idea how to solve a new problem. And this chart shows you that problem crystal clear. On the left, you've got your amazing training accuracy. On the right, your much, much lower test accuracy. That space between them, that's what we call the generalization gap. And our entire goal as ML engineers is to close that gap. The techniques we're about to cover are all designed to do exactly that, even if it means, and this is key, even if it means making our training accuracy a little bit worse. So where do we start? Well, we start with what is probably the simplest, most intuitive, and often one of the most effective tricks in the entire book, early stopping. It's pretty much exactly what it sounds like. The idea is just so simple. While your model is training, you keep an eye on its performance on a separate validation set. That's data it isn't being trained on. You just watch that validation error. And the second it stops getting better and starts to tick back up, you just stop. You hit the brakes. We're basically finding that perfect sweet spot right at the bottom of the error curve. We grab the model from that exact moment, not from later on when the training error might have been even lower. By just stopping early, we physically prevent the model from going too far down that path of memorizing noise. It's brilliant because it's so simple and it works surprisingly well. All right, our next strategy is a bit more direct. Instead of just stopping the process, we're actually going to go in and change the rules of the game for the model. We're going to directly attack its complexity by penalizing it for having large internal parameters. The core idea here goes all the way back to Occam's razor. Simpler explanations tend to be better ones. In the world of models, a simpler model is often one with smaller weights. So what we do is we add a penalty to our cost function that punishes the model for having big weights. We're essentially telling the model, look, I want you to solve this problem, but you have to do it using the smallest, most elegant set of weights you possibly can. The most common way to do this is called L2 regularization, or you'll often hear it called weight decay. We just add this little term to our loss function. And this term is based on the sum of the squares of all the weights in the model. That squared part is really important. It means that L2 really doesn't like large weights and it penalizes them heavily, which pushes the model towards solutions where the weights are all kept nice and small. And the effect of this is really profound. L2 encourages the weights to be small and spread out, or diffuse. The model can't just find one really predictive feature and put a huge weight on it. Instead, it's forced to spread the love and use a little bit of information from all the features. This makes it way more robust and creates a smoother, more generalizable model. Now, for a really interesting alternative, L1 regularization. Take a close look at that penalty. Instead of squaring the weights, we're just taking their absolute value. It seems like such a tiny, insignificant change, right? But the outcome is totally different. Because here's what L1 does. It encourages sparsity. The math just works out in a way that L1 actively pushes the weights of any features it deems unimportant to go to exactly zero. This is amazing. L1 is basically doing automatic feature selection for you. It creates what we call a sparse model, which can be simpler, faster, and way easier to interpret. So, as an engineer, when do you pick which one? Well, it really depends on what you're trying to do. If you think a lot of your input features are probably useless and you want to find the important ones while building a simpler model, L1 is your best friend. But if you think all your features are probably useful and you just want to prevent the model from getting too complex, L2 is usually the safer, more stable, and more common choice. Okay, so far we've talked about stopping a model or constraining it, but what if we try something completely different? What if instead of trying to build one perfect genius model, we just combined the predictions from a whole bunch of different models? This is the big idea behind what we call ensemble methods. The classic example here is bagging. It's a pretty simple idea. You just train a whole bunch of models in parallel, but you give each one a slightly different random slice of your training data. Then, when a new data point comes in, you let all the models vote, and you take the average prediction. It's basically the wisdom of the crowd, but for machine learning.
And the reason this works is just beautiful statistics. The crowd's answer is pretty much guaranteed to be at least as good as your single best expert. But the real magic happens when the different models make different kinds of mistakes. If one model gets something wrong, the others can outvote it and correct the error. But there's a big practical problem. Training even one big neural network can take forever. Training hundreds? That's just not going to happen for most of us.
And that brings us to Dropout. This is, without a doubt, one of the most clever, most effective regularization techniques ever invented for neural nets. It's basically a super cheap, super efficient way to get all the benefits of a massive ensemble. Here's how that works. During training, for every single input, you randomly just turn off a bunch of neurons. You just set their activations to 0.
So what is this actually doing? Every time you drop out different neurons, you're creating a new, slightly different, thinned-out version of your network. And you do this for every single training step. So over the entire training process, you are effectively training an enormous collection, we're talking an exponential number, of different networks that all happen to share weights. It's a brilliant hack.
Okay, so training is this chaotic process of turning neurons on and off. But what about when you actually want to make a prediction? Well, at test time, the party's over. Use the full, complete network with all the neurons turned on. But you scale down the weights to account for the fact that they were only active part of the time during training. This gives you the effect of averaging the votes from that massive implicit ensemble. And the real reason this works so well is that it forces the network to build in redundancy. Because any neuron could just disappear at any moment, the network can't afford to have any single neuron or pathway be too important. It has to learn multiple ways to detect the same features. This breaks up fragile dependencies and creates a model that is way more robust and generalizes so much better. So when you zoom out, you realize regularization isn't just a technical fix for overfitting. It's deeper than that. It's how we, as engineers, inject our own assumptions and our own beliefs about the problem into the model. Choosing L1 means you believe the solution is sparse. Choosing L2 means you believe a simple solution has small weights, and using Dropout means you believe in the wisdom of the crowd. So the next time you're trying to regularize a model, just ask yourself, what do I actually believe about this problem, and which of these tools best represents that belief?